Quito sits at 2,900 meters above sea level, trapped in a narrow Andean valley where the existing airport's single runway ended just 400 meters from a mountainside. For decades, that geometry forced weight restrictions, departure ceilings, and a list of aircraft that simply couldn't risk the approach. Building a new international airport meant finding flat land in a country that doesn't have any. Ecuador's government announced the project in 2003 with a promise that felt engineered for a press release: a modern hub capable of handling wide-body jets, built to international standards, open 24 hours without the noise curfews that choked the old terminal. The only site large enough sat 40 kilometers east, on a plateau near the town of Tababela. Surveys confirmed what engineers already suspected. The plateau wasn't flat. A volcanic ridge called Catequilla rose directly across the planned runway alignment, and moving the site would have pushed aircraft into restricted airspace over an active volcano. The airport could go somewhere else, or the mountain could go. Catequilla wasn't a symbolic obstacle. It stood 65 meters above the runway grade at its highest point and stretched across nearly 2 kilometers of the site. Flattening it required removing more than 20 million cubic meters of material, a volume large enough to bury a mid-sized city neighborhood under 10 meters of rock. The project hired Canadian engineering firm Ecom and a consortium led by Andec, but the work itself fell to earth-moving contractors who had never operated at this altitude or this scale. Volcanic tuff and andesite don't blast or excavate like sedimentary rock. They fracture unpredictably, and the thin air at 2,400 meters cuts equipment power by 15 to 20%. Oxygen deprivation affects not just machinery, but the workers themselves, slowing reaction times and reducing the safe duration of shifts. What looked on paper like a large but conventional earthworks job turned into something closer to high-altitude mining. The first attempt followed standard open-pit logic: drill, blast, load, haul. Contractors brought in hydraulic excavators and articulated dump trucks, running round-the-clock shifts to hit a target of 50,000 cubic meters removed per day. Within 3 months, the schedule collapsed. Equipment breakdowns doubled. Haul roads turned to mud during the rainy season, and trucks couldn't climb the grade when loaded. Dust from the crushers drifted into Tababela, and residents blockaded the access road twice in the first year. By mid-2006, the project was 8 months behind, and less than a third of Catequilla had been moved. Engineers calculated that at the current pace, removing the ridge would take another 4 years, pushing the airport opening into the next decade and threatening the financing structure that made the project possible in the first place. The turning point came when engineers stopped thinking about excavation and started thinking about fill. The airport didn't just need the ridge gone. It needed a runway platform 1,600 meters wide and 4,000 meters long, built to withstand seismic loads in one of the most active fault zones in South America. Every cubic meter removed from Catequilla could be crushed, graded, and compacted into the foundation of the platform itself. The mountain became the airport. Contractors shifted from hauling material off-site to a continuous conveyor system that moved crushed rock directly from the excavation face to the fill zone, eliminating the truck bottleneck entirely. The change required new equipment, new logistics, and new contractors willing to work on a system most had only seen in large-scale mining operations, but it cut the projected timeline in half. The system ran on a scale most infrastructure projects never approach. A primary crusher sat at the base of Catequilla, fed by a fleet of excavators working in coordinated benches. Rock entered at boulders and left as graded aggregate. A network of conveyors, some more than a kilometer long, carried material across the site at up to 800 tons per hour. Spreading and compaction equipment worked in waves behind the belts, layering and testing the fill in 30-centimeter lifts. The entire operation generated its own microclimate, a permanent dust cloud visible from Quito on clear days, and burned enough diesel to run a small thermal plant. Quality control teams tested each lift for density and moisture content before the next layer went down, creating a foundation more uniform and predictable than anything that would have existed if they had simply poured concrete over the native terrain. The budget reflected the ambition and the trouble. Initial cost estimates placed the project at $600 million. By completion, the figure had grown to around $800 million, with earthworks accounting for nearly a quarter of the overrun. Part of that came from underestimating the volcanic rock, which required more energy to break and more passes to compact than the consultants modeled. Part came from delays. Workers went on strike 4 times over wage disputes and safety conditions, halting production for a cumulative 9 weeks. And part came from something no one planned for. Catequilla sat on a pre-Incan archaeological site. Salvage excavations mandated by Ecuador's Heritage Ministry added 7 months and $16 million to the timeline. Pottery fragments, ceremonial platforms, and alignment stones emerged from the benches as the excavators cut deeper, forcing a parallel operation that documented what was about to disappear. Opposition didn't disappear when the conveyors started running. Environmental groups argued that the dust suppression systems failed to meet the project's own standards, and independent air quality monitoring in Tababela recorded particulate levels 3 times higher than baseline during peak construction. Indigenous leaders pointed out that Catequilla had been a ceremonial site for 1,000 years, and its removal erased a landscape feature that connected oral histories to physical geography. The mountain had served as a solar observatory, its ridgeline marking solstice alignments that informed agricultural cycles. That function disappeared the moment the first bench was cut. The government's response acknowledged the loss, but emphasized economic necessity. Ecuador needed the airport to compete regionally, and no other site existed. Whether that trade-off was justified depends entirely on who you ask and what you think an airport is worth. Mariscal Sucre International Airport opened in February 2013, 9 years after construction began and 2 years behind schedule. The runway stretches 4,100 meters, long enough for any commercial jet in service. Catequilla is gone, replaced by a platform of its own stone, compacted to 98% density and rated for a seismic event up to magnitude 7. The airport handled 5.4 million passengers in its first full year and now serves as the primary gateway to the Galapagos, a route the old terminal couldn't support. Tababela grew from a village of 3,000 to a commuter town of 12,000, most of them employed directly or indirectly by the airport. The economic impact studies commissioned by the government claim the facility generates over $1 billion annually in regional economic activity, though those figures include indirect effects that are difficult to verify independently. The engineering worked because the problem was reframed. You don't move a mountain by hauling it away. You move it by turning it into the thing you're building. That approach saved time, cut costs, and created a runway foundation more stable than anything poured or imported could have been. It also destroyed an irreplaceable landform and left a town breathing construction dust for 7 years. Both of those facts are true, and neither one cancels the other out. The airport exists because Ecuador decided the mountain was worth less than what could be built in its place. Everything else follows from that. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.